This is chapter 1. First question. Naturally occurring argon consists of three isotopes, argon 36, argon 38, and argon 40 in the ratio of 4.86 to 1 to 1423. Calculate the percentage of each isotopes. So in total, we'll have to calculate the percentage abundance of three isotopes. So for the first one, argon 36, we'll have to take the relative abundance that is given, and from this question it's given in the style of ratio, so that's what we'll be using. So we'll take the relative abundance and we'll divide it by the total. So we plus 1.46, 4.86 plus 1 plus 1423, and then we times it by 100%, and you will get 0.34%. Next, percentage abundance of 38, argon 38. So again, we'll take the relative abundance, so that is 1, and we'll divide it by the total times 100%, so you'll get 0.07%. Okay, lastly, we'll do argon 40. So again, we'll take the relative abundance given, which is 1423, and we'll divide it by the total, and then times by 100%, so you'll get 99.59%. Next, calculate the relative atomic mass of argon. So to calculate the relative atomic mass, we will first have to find the average atomic mass with the formula KMPK. So we'll just have to sub in the values. So 4.86 times 36 plus 1 times 38 plus 1423 times 40 over the total relative abundance. This will equal to 39.98 AMU, and this is very important. You must write the SI unit. Now to calculate the relative atomic mass, you'll get the same value, except what you want to do is get rid of the SI unit. So we will divide it by carbon, and then you will get 39.98. Okay, next question. An organic compound DD contains only carbon, hydrogen, and oxygen with a mass composition of 41.4% carbon, 3.47% hydrogen, and 55.13% oxygen. If 0.05 mole of this compound weighs 5.8 grams, determine its empirical and molecular formula of DD. Okay, to calculate empirical or molecular formulas, we must always first find the mass of each element. They have not provided us with the mass, but they have provided us with the mass composition and in percentage form also, which means in total it would be 100%. So we have to make an assumption here. So we'll assume that the mass solution is 100 grams. Mass solution, so it's a combination of everything here, the mass of everything, which is 100 grams, so that you can calculate the mass solute for each element. Okay, so first for carbon, you would have to sub in the percentage 41.40%. You sub mass solution as 100 grams, and you have to times it all with 100%. So the mass solute will equals to 41.40 gram. So the same thing for hydrogen and oxygen, except the percentage is changed, and so you'll get 3.47 grams for hydrogen and 55.13 grams for oxygen. And then we proceed by drawing this table that we have learned in our high school. So it's just the same. We do elements first, and then we do the mass, and then we'll have to calculate the number of mole, so that this is basic. So it's mole, it's mass divided by molar mass, so you'll get your mole, and you do it for each one, and then you'll divide each of these by the smallest value. So the smallest value here is 3.45. So 3.47 will be divided by 3.45, and 3.45 will also be divided by 3.45, and you'll get 111. So the empirical formula of DD is CHO. And then to calculate the molecular formula of DD, you have to find the relative molecular mass. To calculate the relative molecular mass, you take the mass and you divide it by the mole, and then you'll get 116 gram per mole. So the molecular formula is written as CHO with a bracket N, and it's equal to 116, and you sub each element with their molar mass, and you'll get N equals to 4. So thus molecular formula of DD is C4H4O4. Okay, now we'll proceed to C. A 25 milliliter of 0.05 m silver nitrate solution is mixed with 25 milliliters of 0.05 m of calcium bromide solution to give 0.105 gram of solid silver bromide and calcium nitrate. So I write the valence chemical equation. First, we will write out everything that was given. So here it's silver nitrate plus with calcium bromide, which produces silver bromide and calcium nitrate. Okay, and then next we'll have to balance it. So we'll check one by one left and right to see if it's equal. So first we'll see the most obvious ones, BR2 here and BR here. So of course we'll have to add a 2 at the front to balance it out. And then also nitrate 2 and just nitrate here. So we'll add a 2 in front of that also. Okay, now let's recheck everything. 2Ag, 2Ag, 2NO3, NO32, Ca, Ca, Br2, 2Br. So everything is equal to each other. So this is the balanced chemical equation. Okay, for C2, we have to determine the limiting reactant. So in order to do that, first you have to find given, needed, and then compare. So given, and this is all mole, of course. So first we find the number of mole of both reactants, so which is silver nitrate and calcium bromide. We take what is given, which is molarity and volume, and we times it to get number of mole, and of course divide by 1000 because they gave us the volume in milliliter. So you'll get 0.00125 mole given for AgNO3 and the same for CaBr2. Okay, and then we'll calculate the needed mole. So from the balanced chemical equation, we know that 2 mole of AgNO3 reacts with 1 mole of CaBr2. So that's why here we write 2 mole AgNO3 reacts with 1 mole CaBr2. So we'll take 0.00125 mole and we'll divide it by 2 to see how many mole that we actually need. And so we'll get 0.00625 mole CaBr2 that is needed. And then we'll compare. So the given CaBr2 is bigger than the needed CaBr2. So this means that it's a excess reactant, and thus AgNO3 is the limiting reactant. Okay, Last but not least, we'll have to calculate the percentage yield of silver bromide. So the formula for percentage yield is actual yield over theoretical yield times 100%. So the actual yield has been given to us, which is 0.105 gram. And so now all we have to find is the theoretical yield. To find that, first we have to compare and find the mole. So we do a from the equation, 2 mole of AgNO3 produced through 2 mole of AgBr. The reason why we use AgNO3 is because it's the limiting reactant. Okay, continuing. Thus 0.00125 mole AgNO3 produce 0.00125 mole of AgBr. And then we'll have to calculate the mass. So we just take the mole and we times it by the molar mass, and we'll get our mass of AgBr, which is 0.2347 grams. And we'll just put it inside the formula, and then we'll get 44.74%. Thank you.